Okay, so you want to get up to speed quickly on some really interesting stuff, right?
To the point, basically.
Yeah, exactly. You want to know what matters without, slogging through a ton of detail.
I want those golden nuggets.
Yes, those aha moments, but without feeling like your brain needs, a week to recover.
Total system overload.
Right, exactly. Yeah. So this time around, you've pointed us to a pretty pivotal paper.
Yeah, really interesting one.
The 2023 paper on QLoRA by Dettmers and his team.
Yeah, it's quite technical, no doubt, but
a little dense.
But super important, we think.
Definitely, and the implications are huge. So that's what we're going to unpack today.
Yeah, we're going to, try to cut through the jargon and get to what really matters for you.
So for this deep dive, we're tackling the challenge of fine-tuning large language models. And, listeners know the power of these LLMs, right? Like LLaMA or T5.
Yeah, they can do some pretty amazing things.
But to really unlock their full potential for specific tasks, you often need to fine-tune them, tailor them to your specific problem.
Right, make them experts in your area.
Exactly. But there's been a big roadblock traditionally, right? Doing that well has required massive computational resources.
Yeah, the kind that most of us only dream of having access to.
Yeah, like a whole server farm.
Exactly. And the paper kind of lays this out, right? The standard way of fine-tuning these huge models using 16-bit precision comes with a really big memory cost.
Like how big are we talking?
Well, they give this example of a 65 billion parameter LLaMA model. And just to fine-tune that the old way, you'd need over 780 gigabytes of GPU memory.
Wow, that's like way beyond most gaming PCs even, right?
Yeah, I mean, that's more than most high-end setups, let alone like a typical research lab.
Okay, so that's a big problem, right? Because it means most people can't really experiment with fine-tuning these really powerful models.
It creates a real barrier to entry.
Yeah, and we know that reducing the precision of a model's weights, what's called quantization, can help when you're just using a model for inference, like to generate text or answer a question.
Yeah, you can get away with lower precision and it still works pretty well.
Right, but as this research points out, those same quantization methods, they tend to break down when you try to actually train the model or fine-tune it.
It's like the math just doesn't work out the same way.
Yeah, so we've been in the situation where the biggest and most capable models are also the ones that are kind of the least adaptable for most folks.
The hardest ones to actually work with.
Exactly. And this is where QLoRA comes in and really changes the game.
This is the big breakthrough.
Yeah. Their core achievement, and what makes this research so significant, is that they found a way to fine-tune that same massive 65 billion parameter LLaMA model.
On a single GPU.
Yeah, just a 48 gigabit GPU readily available.
And not just that, but they actually match the performance you get from the full 16-bit fine-tuning process.
That's mind-blowing, right? It's like going from needing that whole server farm down to just a single high-end graphics card.
It really opens up the possibilities.
Yeah, it has huge implications for who can actually work with and improve these cutting-edge models.
Makes it much more democratic.
For sure. So the big question for us today is, how do they do it? What are the key innovations that allow QLoRA to make fine-tuning large language models so accessible without compromising on performance?
Yeah, let's dig into the nuts and bolts a bit.
Okay, so what's the first secret ingredient in their magic sauce?
Well, the first thing is this new data type they developed called 4-bit NormalFloat, or NF4. And this is really clever because it's not your typical 4-bit integer or standard floating point number.
Okay, so what's so special about this NF4?
It's specifically designed to be super efficient for representing data that follows a normal distribution, the bell curve.
Oh, right, the classic bell curve we all saw in stats class.
Yeah.
So why is that relevant here?
Well, it turns out, and they actually did some statistical analysis to back this up, that the weights within these pre-trained neural networks tend to settle into a pattern where their values are kind of distributed around 0 in a roughly normal shape.
So like most of the weights are clustered around 0, with fewer weights having really extreme positive or negative values.
Exactly. And because NF4 is tailored to this kind of data spread, it can represent these weights much more accurately in just 4 bits compared to those more generic 4-bit formats.
So it's like they're exploiting the inherent structure of these models to find a much more efficient way to represent the knowledge that's in those billions of weights.
Exactly. A really insightful optimization.
It's like having a custom-made suit versus something off the rack. It just fits better, right?
Much better.
And the paper actually shows some really interesting results. They compare NF4 to those standard 4-bit floats and integers and look at things like zero-shot accuracy and perplexity, which is a measure of how well the model predicts the next word.
And you can really see the advantage of NF4, right?
Yeah, Figure 3 and Table 2 show that NF4 consistently beats those standard formats across different model sizes.
So it's not just a theoretical advantage, it actually works better in practice.
Okay, so NF4, that's the first piece of the puzzle. What's the second innovation that helps them save so much memory?
The second big one is what they call double quantization, or DQ, and you can think of this as like squeezing even more memory savings out of the model that's already been compressed with NF4.
Double the compression. That's pretty wild. So how does this double quantization actually work?
So remember when you convert those original high precision weights down to 4 bits, you use these scaling factors, right, to minimize the loss of information.
Like each block of weights gets its own scaling factor.
Exactly. But those scaling factors themselves take up memory. So what double quantization does is it then quantizes those scaling factors. It's like compressing the compression instructions.
So it's like a second layer of optimization on top of the first one. Very clever. So what level of precision do they use for this second round of quantization?
Well, in QLoRA, they quantized those first-level scaling factors down to 8-bit floats using a block size of 256. And they found that this didn't seem to hurt performance at all, which aligns with what other research has shown.
So they're getting even more bang for their buck in terms of memory savings without any noticeable downsides.
Exactly. And how much memory does this actually save us?
Yeah, that's the key question.
On average, it shaves off around 0.37 bits per parameter, which might not sound like much individually, but when you're dealing with billions of parameters, it adds up.
Yeah, it's like those pennies you find on the street. They eventually add up to real money.
Exactly. And for a 65 billion parameter model, they estimate this saves about 3 gigabytes of memory, which, as we saw earlier, can make all the difference in fitting these models onto a single GPU.
Every bit counts when you're pushing the limits of your hardware, right?
Absolutely. And you can actually see this in Figure 3 of the paper. They show how double quantization allows them to squeeze even larger models onto those limited GPUs without hurting performance.
Okay, so we've got NF4 for efficient weight representation and double quantization to reduce the overhead of that representation. What's the third key piece of their approach?
The third one is paged optimizers, and this is a really smart way to deal with those sudden spikes in memory usage that can happen during fine-tuning.
Oh yeah, those memory spikes can be a real pain.
Especially when you're using gradient checkpointing, which is a technique to save memory by only storing some gradients and recalculating the rest when you need them.
Yes, gradient checkpointing, a useful but sometimes memory-intensive trick. So how do these paged optimizers help with that?
Well, they take advantage of a feature on NVIDIA GPUs called unified memory, which essentially lets data move back and forth between the GPU's super fast memory and the computer's main RAM.
So it's like using both types of memory as needed.
Exactly. And what the paged optimizer does is it manages the memory used by the optimization process in this sort of page space. So if the GPU starts running low on memory during a peak, the optimizer states can be temporarily moved over to the CPU RAM and then brought back to the GPU when they're needed to update the model's weights.
So it's like a safety valve preventing those out-of-memory errors that can bring the whole training process to a screeching halt.
Precisely. And it gives you some peace of mind knowing that you're not going to run into those errors.
But doesn't all this moving data back and forth between the CPU and GPU slow things down?
That's a good question. And surprisingly, the paper found that for reasonable batch sizes like 16 for that 65 billion parameter model on a 48 GB GPU, they didn't see much of a performance hit compared to regular optimizers.
Wow, so you get the best of both worlds. You get the memory savings without sacrificing speed.
It's a win-win.
Definitely. Okay, so to recap, we've got these 3 really clever techniques. NF4 for efficient weight representation, double quantization to further shrink the memory footprint, and paged optimizers to handle those tricky memory spikes.
Working together.
Now, how do these all fit together in the actual fine-tuning process using QLoRA?
So the process is actually quite elegant. They start with a pre-trained language model that's been quantized to 4-bit NF4, and then they freeze it, which means its weights are no longer being directly updated.
Okay, so the core model is essentially fixed.
It's like the foundation is set, and then they add these small trainable modules called low-rank adapters, or LoRA, to various layers within the model.
We've heard of LoRA before. It's a way to do efficient fine-tuning by only training these small adapter layers while keeping the vast majority of the model frozen, right?
Exactly. And the key thing with QLoRA is that during fine-tuning, those gradients are backpropagated through the quantized weights of the frozen model, but only the parameters within those tiny LoRA adapters are actually being adjusted and learned.
So you avoid the computational cost of updating all those billions of parameters in high precision.
Huge efficiency gains.
But how does the model actually use those low precision weights during the forward pass when it's generating text or during the backward pass when it's learning?
Right, so this is where the distinction between the storage format and the computation format becomes important.
Okay, so tell me more about that.
QLoRA uses that super efficient 4-bit NF4 to store the model's weights, which is how they get those big memory savings. But when those weights are actually needed for the math during the forward and backward passes, they're temporarily converted back to a higher precision format, typically bfloat 16, just for those computations.
So it's like storing your tools in a super compact way, but then unfolding them to their full size when you actually need to use them.
That's a great analogy.
And the paper really emphasizes that they need to apply these LoRA adapters to all the linear layers within the transformer blocks of the model. Why is that so crucial?
They actually found that just applying LoRA to certain parts of the attention mechanism, which had become a common practice, wasn't enough to get the full performance benefits, especially for those larger models.
So it's about making sure there's enough flexibility for adaptation throughout the model's architecture.
Exactly, and you can really see this in Figure 2. They show that adding LoRA to all those linear layers lets them match the performance of that full 16-bit fine-tuning.
So it's not just about making things smaller, it's about making them smaller in a smart way.
Absolutely, making sure you're not losing anything essential in the process.
Right, and QLoRA isn't just some theoretical idea. They actually put it to the test and train some really impressive models.
Yeah, they call this family of models Guanaco.
Guanaco. So tell us about these models. How do they perform?
So they tested these Guanaco models on a bunch of different benchmarks, and the results were really impressive, especially for the larger models.
Like how impressive are we talking?
Well, on the Vicuna benchmark, which is a common way to evaluate chatbot performance, they compared different models to systems like ChatGPT, and the largest Guanaco model got a score that was 99.3% of ChatGPT's performance.
Wow, that's incredibly close.
And they did this with just 24 hours of fine-tuning on a single professional GPU.
That's amazing. And how much memory did these Guanaco models actually need?
So the 65 billion parameter model only needed 41 gigabytes of GPU memory, which fits comfortably on a 48 GB card. But even more impressive is the smallest Guanaco model, which has 7 billion parameters. It only needed 5 gigabytes of memory.
That's tiny.
And yet that smaller Guanaco actually outperformed a much larger 26 GB alpaca model on the Vicuna benchmark.
That's really impressive. It shows that smaller, more accessible models can actually achieve better results than those larger, more resource-intensive ones.
And it really highlights the practical benefits of QLoRA.
Yeah, for sure. And the paper also goes into detail about how they evaluated these chatbots. And one of the things that really stood out to me was that they actually used GPT-4 itself as an evaluator.
Yeah, that's a pretty clever approach, right?
I mean, using one language model to evaluate another language model, it's very meta.
It is. And they use GPT-4 to generate these ELO ratings for different models by having it judge pairs of model responses for a given prompt and essentially decide which response was better.
So like a language model referee.
Exactly. And they found that there was generally good agreement between GPT-4's evaluations and those done by human annotators, although there were some cases where they differed.
So it seems like using a powerful model like GPT-4 can be a cost-effective way to evaluate other models, but it's not a perfect replacement for human judgment.
Right, it might have its own biases or limitations.
For sure. And another important finding from the paper was the crucial role of the data used for fine-tuning. Right.
Yeah, that's a really important point.
Yeah.
They found that the quality of the training data matters much more than just the quantity.
So it's not just about throwing a ton of data at the model.
Exactly. They compared models trained on a smaller but higher quality data set to models trained on a much larger data set. And the models trained on the better data actually performed better on those chatbot benchmarks.
So it's like with cooking, right? It's not about how much food you use. It's about the quality of the ingredients.
Exactly. And they also found that strong performance on one type of benchmark didn't necessarily translate to strong performance on chatbot-specific benchmarks.
So like a model that's great at answering multiple choice questions might not be as good at having a natural conversation.
Exactly, which highlights the importance of testing models on tasks that are relevant to how you actually plan to use them.
Right. You want to make sure you're using the right tool for the job.
And in addition to all the quantitative metrics, they also did some really interesting qualitative analysis where they looked at specific examples of Guanaco's abilities and limitations.
So like digging deeper into what the model can actually do.
Exactly. And for factual recall of common knowledge, the models actually did pretty well, but their accuracy dropped off when they were asked about less common or more obscure facts, even though they often sounded very confident in their wrong answers.
So like the classic hallucination problem that we see with these models.
Right. They make things up sometimes and sound very convincing while doing it.
And how did Guanaco handle misinformation or those kind of nonsensical prompts?
Well, interestingly, it showed some resistance to certain types of misinformation, like in their flat Earth example, it strongly rejected the premise, and it was also good at recognizing when it couldn't answer a question, like when asked, what time is it, or where are you?
That's good. At least it knows its limits.
Yeah, knowing what you don't know is an important skill for AI.
But were there any areas where it kind of struggled?
Yeah, the consistency of its refusal behavior seemed a bit unreliable. Sometimes it refused to do something based on a weird grammatical justification, and in other cases it could be tricked into revealing information that it was supposed to keep secret.
So it seems like there's still work to be done on making these models more reliable and aligned with our intentions.
Definitely. And they also found that math was a weakness for Guanaco, which is a common problem for these language models. They can sometimes accurately solve multi-step problems, but then fail on seemingly simple tasks.
It's interesting how these models can have such a mix of strengths and weaknesses.
And being able to do these kinds of qualitative analyses on such large models is a big step forward thanks to the efficiency of QLoRA.
It lets us really understand what these models are capable of and where they still need to improve.
Exactly. And it also points to some broader implications that go beyond just achieving better scores on benchmarks.
Yeah, like what are the bigger picture implications of all this?
Well, the most significant one is the potential for democratizing access to large language model fine-tuning. Because QLoRA reduces those memory requirements so drastically, it makes it possible for smaller research groups, companies, and even individuals to fine-tune these powerful models.
That could really level the playing field and lead to a lot more innovation.
Exactly. And the paper even talks about the possibility of fine-tuning LLMs directly on mobile phones and other devices.
Wow, that's wild. So you could have a personalized AI that lives on your phone and learns from your interactions without your data ever leaving your device.
Exactly. A really exciting prospect.
Definitely so. So to wrap up our deep dive, what's the key takeaway from this research on QLoRA?
I think the big takeaway is that QLoRA is a major breakthrough in how we fine-tune large language models by combining these clever quantization techniques with smart memory management. They've made it possible to fine-tune these incredibly powerful models using readily available hardware and without sacrificing performance.
And that has the potential to open up a whole new world of possibilities for how we use and interact with these models.
Absolutely.
So hopefully you came to us wanting to understand this important research without getting lost in the details. And now you have a solid grasp of the key concepts behind QLoRA and its implications.
Yeah, and it really raises an interesting question for you to ponder what new and maybe unexpected applications of these personalized and fine-tuned language models might become possible now that QLoRA has made them so much more accessible.
It's an exciting time to be following this field, that's for sure.
Absolutely. There's so much potential for innovation and discovery.
So we encourage you to explore the released models and code and see what you can come up with. The possibilities are really endless.
And who knows, maybe you'll be the one to discover the next big breakthrough in AI.
That's it for this deep dive. Thanks for joining us.
And keep those brains firing.
We'll see you next time.
Bye for now.